Good afternoon, everyone, and welcome to the Frontier Precision UAS Choosing the Best Tool for the Job webinar. Frontier Precision has 12 offices in 11 states. In terms of UAS, we are national dealers for a number of manufacturers, which you can see here. My name is Phil Johns. I'm joined by Nathan Stevenson out of our Denver office and by Mike Clarenbeek out of our Sioux Falls location. If you have any questions throughout the webinar, please feel free to type them into the question box, and we'll be sure to get to them as quickly as possible. This is the first in a series of webinars brought to you by the Frontier Precision UAS team. Today, we kick off those webinars with choosing the best tool for the job. Next week, we'll talk about UAS and inspections. The following, UAS photogrammetry. We'll end April with UAS for LiDAR. Let's get started. So today we're going to talk about a number of industries that UAS is currently being used in. Mostly in our experience, drones are being used in a number of areas, pretty much anything you can think of between hobbyists and professionals. We're going to dive into the industries that we work on with our customers. We're going to talk about general flight technology, just a brief overview of flight and how it relates to drones and the types of flight technology we use. We'll talk about sensors and payloads that can be attached or sometimes come on board integrated in drones. We will discuss control and GPS correction technology. So dealing with that imagery and aligning it to the correct place on Earth. We'll talk briefly about data processing. Most of that will be dove into later on in our photogrammetry and LiDAR sections. But we will cover it briefly and do some compare and contrast between LiDAR and photogrammetry today. And then just again, also we will dive into this later, but data analysis and interpretation. What do we do with all this data that the drone is giving us that we're collecting with all of the above technologies we're going to discuss? So industries. A few of the industries that we're seeing drones being used in. First, one of the use cases that, again, we'll talk about next week at a deeper level, but inspections. This is everything from utilities to infrastructure, cell phone towers. Drones are being used to do inspections on solar arrays, looking for hotspots with thermal cameras and things of that nature. Even into using thermal for rooftop inspection, insurance, major commercial insurance, rooftop inspection. With the thermal cameras, we're able to see things like water intrusion, things that may not be available to the naked eye. We're able to put some of these sensors that have been used in traditional methods for years, and now we're putting them to the air and covering more inaccessible areas quicker. Public safety. It's another one of the areas that we work quite a bit in. Public safety is using drones for everything under the sun that you can imagine. It's really helping that industry, saving lives, and just making our tax dollars more efficient. So things like search and rescue, using thermography for that, and also high resolution cameras, firefighting, scene reconstruction and documentation. Using both drones and then software like Pix4D React to quickly process imagery and get that information to the boots on the ground. And then also in law enforcement, general incident reconstruction, accident reconstruction, crime scene documentation, things of that nature. We move on to construction, another industry that we're seeing a lot of uptake in UAS. Each of these industries we can dive into quite a bit, and we will individually over the coming weeks. And then eventually we'll also even have specific webinars on some of these industries. So with construction, general progress monitoring, just a picture of what's going on the ground, tracking cut and fill when doing earthworks and earth moving and grading. Being able to calculate those volumes quickly and efficiently. Asset management, just keeping track of inventory and items on a job site. This can also include stockpile volumes of material or any number of things, vehicles, piping, materials that have been delivered to the site, keeping track of where those are at and the movement of those materials. And then that dives into even just quality control. In construction, lots of quality control is necessary. We're dealing with a number of different parties, whether it's contractors or staff, following and tracking work, assigning work, and using that imagery to assist us in doing that. The use case in mining and aggregates is similar to construction, but it does have a few specific differences. Still able to do things like stockpile inventory, but then where the power really comes is when we get into safety compliance, tracking how high berms and blocks are for MSHA. This is a picture of some of the high wall and safety compliance analysis that we did on a mine. All of these individual blocks identified by height compared with the height of the largest truck on site, which is how MSHA rates whether you're in compliance or out of compliance, and giving them an instant view on exactly what's going on site. Analyzing haul roads and making them more efficient. I had a conversation with a friend of mine that I've worked with for years in mining, and they talked about how haul road analysis can affect their industry. I mean, some of these trucks, this one shown right here is a 797 Caterpillar, work out to be just under 1 mpg as far as fuel efficiency. And that's not miles per gallon, that's minutes per gallon. You speed them up over the course of a year by about a mile an hour, and you have millions of dollars in savings. So these are the types of things that we like to promote and show that, not only can we collect good, beautiful looking data, but it's also very usable and it can really change the way we do business. Mining and aggregates is actually starting to use drones for maintenance and inspections as well, even diving into some thermal activity. Looking for hot spots on coal piles, so they're not waiting for a fire to start, but they're actually able to hit it before it initiates. Looking for hot spots on the loader belt wheels, just to see if there's a differential in temperature, to see if there may be a breakdown coming. Real case example, also on a mine that I worked with, they had a Z30 zoom, 30 times zoom lens on a DJI M210 RTK, which we'll talk about in a little bit. And they were able to see from quite a distance away on an inspection a sheared bolt on a loader belt that could have collapsed and caused not only about $100,000 in repair damage, but it also could have taken a life. So, the way that people are using drones, we're excited to see every day evolving. And then general workforce management. This applies to any number of industries, but again, keeping track of what's going on the ground, utilizing that data and communicating. Some of the cloud platforms have chat options to where you can add annotations and communicate about those, export annotation reports, and use them as work orders, essentially. So really changing the face of many industries with that side. Agriculture, forestry, and land management. Each of these three can probably be categorized as completely separate beasts. We put it into a similar category because they use some of the same equipment. So things like agriculture and agronomic condition, plant count, plant health, plant vigor, managing forestry and public use lands. Especially in the West, most of our land is publicly held, so lots of benefit there. Vegetation management in general, and also just noxious and invasive weed control is another big use case, using multispectral imagery and the like. Continuing on the overview, and I know some of this will be pretty high level for some of you. Some of it will give you new information that you might not have known, though. Flight technology. Just want to spend a few minutes on flight, something that as the UAS team we're pretty passionate about. So basics of flight. Flight requires lift. Airfoil, it's a body designed to provide a reaction force when surrounding air passes over it. Just an example of how that happens. Essentially what goes on is we have a low pressure, high speed movement of air on the top of the airfoil, and a high pressure, low speed movement of air on the bottom. In turn, this creates lift. So if we minimize the pressure on top, maximize the pressure on the bottom, we have lift. And so the airfoil is designed to force that air over and create that lift. Most people are familiar with wings. It's made up of a series of airfoils, and they vary the shape of these airfoils to maximize lift over the particular area of that wing. And this is a wing being pushed through the air. The most common way of pushing a wing or pushing a body through the air, or at least the most traditional way, is with a propeller. A propeller is essentially a set of rotating wings attached to a central hub. So what it does when it's spinning fast is it's creating lift. So it's lifting the aircraft forward, for lack of a better term. And then the wings on a plane, when the aircraft is being pushed forward, provide lift. So how does this relate to UAS flight technology? Well, the three most common types of aircraft is what we're going to cover. It covers, I'd probably say, about 99% of the drones out there, if not all of them, some version of these. So, and that would be multirotor, fixed wing, and then a hybrid between multirotor and fixed wing. So let's talk about multirotor. Multirotor is, by definition, just a central body. It has multiple arms with rotors that power horizontal spinning propellers in order to create lift. The motion of this aircraft is controlled by simply varying the speed, the relative speed of these rotors. We're not going to dive into this too deep. There's tons of really awesome, fun science. I encourage you to look into it and learn more about this technology. But the main thing we want to concentrate as far as with UAS is that what this allows is extremely accurate maneuverability. The aircraft, similar to a helicopter, is going to vertically take off and land. So that's VTOL, vertical takeoff and landing. It gives it 360-degree maneuverability. It can climb, it can drop in altitude, left, right, any motion that you could desire, you can essentially achieve. So very, very accurate. And it has the ability to simply hover in place. So when we're dealing with inspections and zooming in from a really long distance, or trying to do search and rescue and find someone or pin in on something, that hovering really comes into play. While you do have the benefit of the maneuverability on a multirotor aircraft, you do have the drawback of area of coverage. Multirotors generally are about half the flight time of a fixed wing. So something to consider. They will cover, with that reduced flight time, much less area. So while you do have the benefit of the maneuverability on a multirotor aircraft, you do have the drawback of area of coverage. Here's an example of a multirotor we carry. This is my personal favorite. The M210 RTK also comes in a non-RTK version. This is our workhorse that we use religiously on most of the jobs we're doing with a multirotor. Tons of great information there. Feel free to dive in or ask us questions later, but we can move on from here. All right, fixed wing. So the next type of aircraft is fixed wing. This is what most people are familiar with in flight as a plane, whereas most people are familiar in drones with a multirotor. Fixed wing is made its place in the UAS world. Similar to a plane, one or more vertically spinning propellers provide forward thrust or forward lift. The fixed wings on either side of a central body change the pressure and direction of the oncoming air to create lift. And then we control motion, left, right, climbing, diving, by adjusting the lift force that each wing receives. We do this by simply changing the shape of the wing itself. As you can see here, each wing has an aileron. The aileron is responsible for changing the shape of the wing. If we provide more lift on one side, the aircraft will turn. If we provide more lift on both wings, then the aircraft will climb. And if the ailerons go upwards and provide more drag, then the aircraft will descend. When we get into the fixed wing technology, because it's using wings to create lift, and it's actually, the closest thing to flying that we can call it, where a multirotor is really just holding itself up in the air. the fixed wing is actually flying. So this increases the efficiency of the power being used by the motor, and in turn increases the flight time. While we're on fixed wing, the aircraft that I showed is the DLR UX-11, one of a few fixed wings that we carry. We have a flight time of about 59 minutes. With that 59 minutes, we can cover about 250 acres at a 1 centimeter ground sample distance, or about 520 acres if we're flying at that 400-foot FAA ceiling, and we're getting about 1.7 centimeters ground sample distance on that. So substantially more. I'd probably say about 5 to 7 times the area of coverage as compared to the M210 that I showed you in a single flight. And then we move on from multi-rotor and fixed wing into the world of the hybrid. Hybrid is kind of the new kid on the block. It's not new to aviation. It's been around for years in aviation in general for manned aircraft, but it's fairly new to the UAS flight technology world. And when I say fairly new, we're talking a handful of years. It's not a year or less or anything, but it is the newest kid on the block. The idea here is it utilizes multiple rotors. Sometimes those rotors will be will adjust themselves, as you can see here on the Quantum Trinity. Those rotors will turn upwards. Those spinning propellers that are turned upwards provide that lift in the exact same way that a multi-rotor. I mean, essentially we are using multiple rotors. So it is a multi-rotor on takeoff and on landing. But once it's in the air, it makes a transition to forward flight. And what this does is it allows the motors, for example, on the Quantum Trinity, those front two motors actually fully shut off, and only that rear motor turns forward. And well, they all turn forward, but the rear motor stays on. And that provides that forward thrust, and the wings and the efficiency of the aerodynamics of the aircraft are what keep it in the air. And so what this does is it really increases that flight time like a fixed wing, but it gives us the accessibility and the maneuverability closer to a multi-rotor. It's not going to be the same maneuverability as you would have like on the Matrice 210 or a Phantom 4 Pro or any of the other multi-rotors that we have out there, but it does have the advantage of those wings, and so it does increase that flight time immensely. This is also known as a fixed wing VTOL. You might hear it called out there. But the idea is that we have a vertical takeoff and landing and a horizontal fixed wing flight. Showed you the Quantum Systems Trinity there. It's the baby brother. And really, I would say a competitor for the DLR UX-11 that we also carry. The Quantum Systems Tron is another one of our favorites. This is the big brother. This has the benefit of actually carrying much heavier payloads. It can carry LiDAR, YellowScan Surveyor Ultra. I actually left off. It also carries a visible spectrum payload with the Sony RX1R2, or I'm actually getting that wrong. I'm sorry. That's on the Trinity. I apologize for that. But you basically can switch out between these two payloads. You cannot have a dual payload, but you can have a single of each one. As you can see, the capabilities of this aircraft are pretty insane. It has a 90-minute flight time. Looks like the coverage got cut off there, but this aircraft can cover about 3,000 to 4,000 acres in a single 90-minute flight. That's not a misspeak. 3,000 to 4,000 acres in a single 90-minute flight, whereas the Trinity can cover roughly about 1,400 acres, about 1,400 acres in a single flight. All right, let's move on and talk about some sensors and payloads. So as you can see, a number of different options. These are just probably the main ones that we carry. There's one on here that's no longer available, but we'll talk about that. Basically, a sensor or payload is something we attach to the drone. It is the camera. It is the agricultural granule spreader. It is the noxious weed herbicide sprayer. It is the thermal sensor. It is the LiDAR unit. So we're going to talk about some of the technologies that go into these sensors and payloads. So two different there's multiple categories, but I'm going to split these up into sections. And those first four, I would call these electro-optical, which means they are using something from the light spectrum. And then the last one that we'll talk about is deployment payloads. So the first four there are RGB, which captures the visual light spectrum of the human eye, infrared or thermal sensors that capture the beyond visible spectrums, but that are basically going to allow us to see thermal differences. Chemical detection sensors, which a lot of people don't know, are actually using still a similar spectrum to the other two. They're just, it's not in the human visible spectrum, but it is technically still in the infrared spectrum. LiDAR, which is light detection and ranging, also using lasers at a specific frequency and wavelength. All right, so just before we dive into that, one of my favorite things, it's actually one of the things on my background, and it's always fascinated me, is how many waves are out there that we have no idea about. The electromagnetic spectrum is a chart here that's showing kind of the span of these different rays. The rays that we're interested in for today's purposes really is the visible spectrum, which is a very, very small part of that, and the infrared spectrum, which is not visible to us, but it is something that we utilize in many of these sensors. So first, talking about the electro-optical red, green, blue, or the visible spectrum sensors. Now you'll see why I added this in just a second. Generally, the most commonly used sensor type is something called a CMOS sensor. And CMOS sensors are capable of picking up generally in the range between 350 nanometers to about 1 micrometer. Now we can't see that, and the near infrared that exists between about 740 nanometers and 1 micrometer, we generally don't want when we're capturing the visible spectrum. Most high-end cameras these days, even though the sensors are technically capable of capturing that near infrared, they will put a filter on to filter out that near infrared light. Now that can benefit us in some ways because there are modifications that we can do sometimes on these cameras to remove that filter and capture that near infrared spectrum. We're not going to get into that today, but just a little bit of information. So when we're talking about the visible spectrum of light that we want to capture on this electromagnetic spectrum, we get into red, green, blue sensors for mapping and for inspection. Again, typically CMOS, and you can dive into this on your own if you'd like, but there's CCD sensors and CMOS sensors. CCD is generally a little more expensive. The integration of CMOS into the world of digital cameras has really made it more accessible and more affordable. Pretty much any major camera that you're getting from Canon, EOS, or any of these cameras you're seeing here, the camera on your digital phone or your smartphone, your digital phone, all of these are mostly CMOS sensors. Again, they're sensitive to wavelengths from approximately 350 to 1,050 nanometers, or 0.35 to 1.05 micrometers. Infrared is generally cut off and filtered out specifically for these cameras for the visible spectrum. We can apply different lenses on certain cameras, not all of them if they're integrated into the system, but for most of these cameras that we're going to talk about, we can apply different lenses for different uses. So we could add a higher, 50 millimeter lens to zoom in really far for an inspection. We can tail that back and put a 24 millimeter lens on for mapping. All right. So just some of these to talk about. Probably the most well-known and, in my opinion, best mass-produced and most accessible drone in history is the Phantom 4 Pro V2. We, as an enterprise dealer, we actually sell the RTK version of this drone. Essentially the same sensor, though. It's a 20 megapixel CMOS sensor, 1-inch CMOS sensor, and the RTK version, it just adds an RTK puck on top of it. We'll talk about what that means in a little bit. That camera, as we moved into the enterprise world and wanted to attach lenses to things like the DJI Phantom, the M210 RTK, like I showed earlier, or any of the other more industrial drones out there, we had a need to attach this camera to another drone. Because the camera, that 20 megapixel CMOS sensor, was so well accepted and so well made, they actually integrated that, DJI integrated that same sensor into the Zenmuse X4S. Same 20 megapixel CMOS sensor. Used to say, unfortunately, this gimbal and camera is no longer made. It's no longer available. Many people are still using it. It is one of the better collection sensors for RGB out there. Now DJI has moved on. They, from there, created the X5S. Unfortunately, the X5S was not a mechanical. It was based on a rolling shutter technology. That's not so much of a problem in mapping as much as it used to be, but it can cause some issues in certain situations. So one of the things that these all have in common, for mapping, we're looking for that global or mechanical shutter versus the rolling shutter technology. As we move forward, DJI now has released probably the best sensor, in my opinion, made for drones. Had some hiccups at the beginning, and we weren't pushing it quite as hard. We were making sure that we tested and verified it, but now we are fully confident in the Zenmuse X7 and feel that it is an incredible product. It's a 24 megapixel CMOS sensor, and it has multiple lenses available for it. The one I'm showing is a 24 millimeter lens. It also has a 16 millimeter lens. Unfortunately, that is made with a rolling shutter rather than a mechanical shutter. So we generally will recommend the 24 millimeter lens for mapping. And then there's a couple of other lenses that we'll generally recommend for inspections. One of the hot kids on the block right now, one of the most exciting cameras out there that many people are using, and now we have an integrated way to put it on the M210 series via the Cloud PPK system that we'll talk about. But this camera, the Sony RX1 R2, got a little 4 in there. That's not supposed to be there. That's just a Sony RX1 R2. It's a 42 megapixel full frame BSI CMOS sensor. BSI is just a little bit of an improvement on the traditional CMOS technology. We're not going to talk about that today, but definitely an exciting camera out there. And so talking about these cameras, I mean, these are getting into, more custom solutions. So the Sony RX1 R2, in order to attach this to a drone, clearly it's not made to be put on UAS, but there are systems that allow us to do that and jump up to that much higher resolution. Again, not so necessary for mapping, but when we're getting into inspections, or if we do want to map a large area in a quick amount of time, instead of flying so low, we can fly quite a bit higher. So it does work quite well for mapping. But then also we get into really high-end cameras. One of them that's being put out right now is by Phase 1 Industrial. It's the IXM100. I mean, this is jumping up to a 100 megapixel sensor. Phase 1 traditionally has made cameras and sensors for manned aircraft to take photogrammetric documentation and pictures from much higher altitude than we're flying with drones. But now Phase 1 has actually figured out a way to integrate this onto units like the M600 by DJI. All right, so moving on from mapping, RGB sensors for inspections. You'll notice the DJI Zenmuse X7 is still there. However, if you're using it for inspections, I would probably either keep it as your visual camera far back with a 24 millimeter and combine it with something like the Zenmuse Z30 that's a 30 times optical zoom. Incredible sensor. Or if you want to utilize that same sensor, you can actually remove the 24 megapixel lens and throw on a 50 millimeter lens, which allows you to zoom in quite a bit further, or at least have that telephoto ability to see much more detailed close-up imagery from a far further distance. Still working in the visible spectrum, we'll talk about multispectral sensors. The main difference between multispectral sensors and what we're looking at with the CMOS RGB single sensor is that multispectral sensors essentially break up and capture each individual spectral band individually. So it will capture red, green, blue, often near infrared. With the Ultim, it actually puts a long wave infrared on there. So it's basically allowing us to break down and separate and record each of these types of data for each band individually. Some of the uses that we have in that, most of this is being used in this day and age for agricultural uses. Some of the things that you're able to see when you break up the different bands is a lot of those use cases that I mentioned in the beginning. Identifying different species of plants, identifying plant health, plant vigor, based on how much nitrogen they have, or if there's more water in one and others have dried out. We can often see that in these individual bands. These are some of the use cases for multispectral. All right, so moving on to the next section, we'll talk about infrared. So infrared is up here, really the infrared thermal sensors. Typically, we're looking at long wave infrared. So infrared can be broken up into a number of different sections of bands. And typically these are used for different purposes because they allow us to visualize, quote unquote, not with the human eye, but through the use of the technology of the sensor and the digital transformation of that, of what it's picking up, we can identify different things. So thermal sensors are working in the long wave infrared spectral band of about 8 to 14 micrometers. Sorry about that. I don't know if you guys can see that pop up. What the heck was that? Sorry about that, guys. Notifications. Okay, I think we're back. Okay, I have to do a little edit there on the delivery of this. Okay, so generally when we're using this for UAS, we want a radiometric type of thermal sensor. We'll talk about this a little more when we dive into the inspections webinar, but the idea of radiometric is it measures temperature by interpreting the intensity of an infrared signal. The FLIR XT was really the powerhouse that came out a number of years ago by DJI and FLIR. It has since been updated and replaced by the XT2. It has the same thermal sensor on it as the XT1. However, what they did is they made this a dual RGB visual and IR thermal sensor. So it picks up the spectral band from a little below what we would consider long wave. It's 7.5 micrometers up to 13.5 micrometers. Can generally detect a differential in temperature between negative 40 degrees and 550 degrees Celsius. So quite a good range there. And then the visual sensor, not the sensor I would probably use to do high-end mapping like the other sensors I showed you, but it does have a pretty good CMOS 12 megapixel sensor on it. And what this does is FLIR has come out with a technology where they actually blend the visual and the thermal together to aid in identification of what you're actually seeing, because many of the things that we would identify, such as text or signage or really a number of things, are not visible in that thermal spectrum. And so the visual spectrum lends as an aid to that. Broad range of uses that we're seeing with thermal, definitely inspection and public safety are the two main industries that have been using this for years. Seeing a lot of uptake in actual, mining and construction maintenance. Looking for things like I mentioned, like hotspots on different pieces of gear or equipment to detect failure ahead of time. One of the interesting uses that we don't really play with either in thermal is in art that I discovered not too long ago, that they can actually kind of see if a painting had been painted over or corrected by the artist. So lots of opportunity in the thermal spectrum and being able to access that. All right, if we move over to the midwave, we can do things that people, even myself, a number of years ago didn't imagine. And one of these things is TD-last methane detection. The spectrum of these sensors generally are between 3 and 5 micrometers. And a couple of manufacturers out there that we're really excited about. Microdrone's M-Detector system. Incredible system, and for the price and what it does, it's actually pretty incredible. It's about the same price, actually a little less expensive than the DJI U10 laser methane gas detection. A little bit different technology, but just kind of gives you an idea. So these laser gas detectors are using something called a tunable diode laser absorption spectrometer. Again, picking up between 3 and 5 micrometers. And essentially what happens is this laser shoots at this particular frequency, and some of that laser is deflected by that particular frequency by the gas, and able to be visualized in our viewer. Mike Clarenbeek, who is one of my UAS cohorts out of South Dakota, actually has done quite a bit of work with the Microdrone M-Detector. Mike, do you want to add anything to your experience with how that system worked and kind of the technology behind it?
Sure. No, it's a pretty slick system. Just like any interface, you have a ground station, and what you'll see real time is basically it measuring the parts per million in the air of whatever gas, methane gas that you're looking for. So if there's a leak, you'll start seeing higher parts per million readings in real time. And then there's also a data logger. So after the fact, you can also put it up on a map and see exactly what your readings were from your laser. So offers a very efficient workflow to find potential gases out in the field, and also after the fact having the data collected so you can go back and better locate those leaks and where they were and document them.
Cool. Yeah, so those two workflows are a little different. The DJI offers a real-time view of the gas. It has a RGB camera that it integrates with that detecting system. And then the Microdrone M-Detector kind of logs what you're doing, and then you can go back and visualize that, which in these situations is pretty much just as useful. So a couple of different things on that. Pretty exciting stuff. All right. Let's see if it's going to let me go forward. Oh, skip past that. All right. And Nathan Stevenson's personal favorite kid in the room, along with probably myself and a few of us here, is talking about terrestrial LiDAR. Terrestrial LiDAR uses a frequency of roughly 1.04 micrometers to 1.06 micrometers. And what it's doing is it's actually creating a physical measurement on the ground with that laser. Here is one of the units that we are most excited about. We use quite a bit is the YellowScan VX-20. And Nathan, are you with us? Do you want to talk about the YellowScan LiDAR just for a brief second and maybe give a plug to your LiDAR talk you're going to do soon?
Sure, I can, sir. I was just unmuting myself there. So the YellowScan system here, and actual aerial LiDAR systems in general, they offer a fair bit increased efficiency for topographic data collections, because as we kind of talked about, you can go airborne It also allows us to have data that's already processed, in the fact that we don't have to reduce images to point clouds. We already have those physical data points collected.
Yeah, and Nathan, I'm actually the next part we have up here is sort of just spending just a moment talking about the next part, which is data processing. And why would we choose photogrammetry versus LiDAR? Again, we're going to cover this at great length in our coming webinars, but I have a couple of slides here, Nathan, that you're familiar with, and maybe you just want to talk just for a moment about those two technologies and sort of kind of the differences briefly, or at least for LiDAR maybe. Okay, it looks like we lost Nathan. All right, so I'll cover that. So LiDAR, as Nathan mentioned, and I mentioned before, LiDAR is a physical measurement. It's actually firing a laser off and capturing a distance from where the UAS unit is in real time. It's very quick, it's very fast for data capture and processing. It captures the data in a similar time period as what you would with an RGB sensor. However, that processing is it's not quite instantaneous, but we're talking, probably about 20 to 30 minutes per flight of data processing, and you have your output. One of the benefits, another one of the benefits is that often the LiDAR laser can penetrate foliage and vegetation. Because it is a physical measurement and it's not essentially interpolating a measurement out of the photos it's taking, like photogrammetry, there is a reduced need for control. In addition, many of these units, especially the YellowScan, have some of the more advanced trajectory correction that we'll talk about in just a moment. So with all the benefits that LiDAR does offer, it does come at a hefty price. It's quite a bit more expensive. It requires a little more skilled operation and processing, at least on the back end. The flight itself is not it's not really dissimilar from a photogrammetry flight. And because of that cost and the reduced amount of manufacturers that are really creating it, it is semi-inaccessible. Repairs, buying new items, things of that nature are a little more inaccessible than the counterpart in photogrammetry and RGB sensors. So photogrammetry, just to talk about that, it's what we're most familiar with. It has its place. It's not going to be at quite the accuracy of LiDAR, but it does achieve the accuracy that is good enough even for many survey applications. I don't know if you guys saw Jay Haskamp's webinar, which will be available in the next couple of days, sort of comparing a real world scenario of a number of different photogrammetry and LiDAR, both UAS based and vehicle based, and shows both accuracies, processing time, and sort of where they fall into the picture on a few different benchmarks, anywhere from 500ths up to a 10th up to a 20th of a foot. And oddly enough, photogrammetry and really all of the collection methods, when we're looking at about 0.2 feet, almost all these technologies are falling above the 95th percentile in accuracy. So photogrammetry is the workhorse for a reason. It's very fast with the data capture. It's quite versatile because it's just very available, and there's a number of different technologies to carry the sensors, which we talked about earlier. It is quite accurate when done correctly. It does require a bit more control and checks. And that's because it's a passive technology. What we mean when we say passive technology is images are processed in order to enable measurements. It's not a physical measurement like LiDAR. Essentially, we're picking points, or the system is picking points. And again, we'll cover this deeper, but at a basic level, we're identifying similar sections or points in different images and creating a photogrammetric map, which you're all familiar with what a map looks like. So we're taking mostly the center section of each of those images and stitching them together. And then beyond that, we're actually utilizing the other parts of the image to create a 3D model. And when we move on from sensors, the last one that I'm not going to spend too much time on, but some of the new and exciting things we're seeing is payloads. So two here are related to agriculture. One is actually a spreader for seeds or granules for mosquitoes. And the other one you're seeing on the right is the AgGrass made by DJI. And it's for precision agriculture spraying from a drone. So pretty exciting stuff. There's also some that have to do with public safety that we'll cover in inspections, and Mike might be able to talk about next week. Okay, so we're running at about 10 minutes. So what I lastly kind of want to cover is control positioning correction, and then just some of our options for data processing. So not going to spend too much time on this, but just to give you a brief idea of the technology. Traditionally, when we started with drones, we didn't really have any GPS correction technology on board the drone. We were using GCPs, or ground control points. With ground control, essentially what we're doing is we're identifying targets that are visible from the air, generally evenly spread about every 1,000 feet or so apart. This is going to yield the best accuracy because what we're doing is we're flying, and then later on we're identifying points in that photo or in those photos that are real places on the ground. And as long as we have evenly spread GCPs, it generally yields the most accurate results, albeit it can be a bit inconvenient. So this is an example of 212 acres with 8 GCPs at that sort of evenly spread 1,000 feet apart. If we move up into a very large site, like 3,300 acres, it starts to get a little silly. We probably wouldn't use quite this many, but it gives you the idea. If we want to achieve that same accuracy as I did on that 212 acre site, this is what our GCP layout would lay out, and it pretty much kills any convenience that a drone is offering. Relative positioning with RTK allowed surveyors, this came out a number of years ago, rather than having a static base station that simply collected data and then moving on to another static location, it allows us to have a single base station that identifies that point and then use relative positioning with a rover that connects to that base station in a very quick amount of time. We're talking a handful of seconds or a couple of minutes to get a very accurate location relatively to the base station. So RTK, while it's something that is religiously used in surveying, with drones, it's a little bit different. Still a very exciting technology, still works in a number of situations incredibly, but when we make the drone the rover, that drone is moving. So if we have something like link loss where we're not connected to that base station for a moment, if there's interference because we're flying near a tower or something that may be causing that signal to be interrupted, whether it be a tree or a hill or whatever it may be, RTK sort of loses its glow with drones at that point because that drone does not stop, it keeps flying, and those images are simply not corrected. With PPK, what this allows us to do is the base station is logging data, the drone is logging data, and then afterwards we post-process that data in order to correct the location of those imageries. So there's no connection required between the base and the drone. Another benefit of PPK is that you can process backwards and forwards. You can add in other things. You can, we'll get into this in the photogrammetric processing, but the idea is that it actually increases your ability to process and reprocess and then try different things without simply having the RTK data tagged and it is what it is. Plenty of PPK and RTK drones out there. Almost every manufacturer these days has a version. One of the new kids on the block for drones, at least, not so new in surveying, but still not as used as the RTK method in surveying, is precise point positioning. What this does is it introduces the geostationary L-band communication satellites. Right now we have 2 of them, and it utilizes reference stations. It corrects the orbit and clock of those satellites very precisely and communicates directly with that rover. So rather than having to have a base station, you are utilizing that system of L-band and full constellation satellites along with the reference stations as your base, and then you are connecting as your rover without a base station on site. What's interesting and cool about this with drones is it essentially negates or at least minimizes the situations where we really need a base station if we have access to this technology. Couple of direct georeferencing manufacturers, that are allowing drone manufacturers to install it in their equipment. Trimble with their acquisition of Planix and the DG. The APX, I think this is the APX-20 that I'm showing here. It's basically has a Trimble Planix GNSS initial board and its own IMU as an enclosed system, and so it provides much more accurate data, and if not negates, it drastically reduces the need for control. Cloud Geomatics is another one that we're quite excited about. This is a modular external system that can essentially be attached to any drone and allows for PPK processing post-flight. This same unit actually has the ability to connect and run PPP or precise point positioning, similar to the Trimble Planix board as well. So data processing, we talked slightly about this. We're going to have a whole webinar on data processing, but just briefly, there's a number of different engines out there. The big kid on the block is Pix4D. One of the platforms we're also excited about is Metashape. A little more inaccessible and expensive, but still a great platform. And then there's Bentley. Couple of different options for processing, of course. When you're processing, you can choose to process locally on your own computer, is the traditional way most people have done it. But there's a new kid as well, and that's cloud processing. So cloud processing is a little different than local processing. Both have their benefits and I would say drawbacks. Local processing, it's sort of choose your own adventure and run with it. You need to get the license, the computer, the training. Platforms like Delair are actually offering the ability to access all of these different engines under one roof without the need for expertise in photogrammetry. Again, we'll dive into this a little deeper, but just wanted to give you guys kind of a taste. Local processing, you do have control over the entire process. You essentially can process an unlimited amount of data if you have a license that allows you to do so. It does require a top-end workstation and extensive training, and your data is secured by yourself. Cloud processing, basically the same idea. You collect the data, control, but then you upload it for processing, and then that processing is done and verified by photogrammetry experts. But it does require quite a good bit of internet and upload time to get that processing going. I'll share this a little later. We're not going to spend too much time on this. It's just a little cost comparison between the two. And then just a little sneak peek on what do we do with all this data in closing. We just have a couple of minutes here. Apologize for taking so long and not getting to the questions today. We will respond directly to your questions via email.
I think we've been able to get, Nathan and myself have been able to get pretty much everyone's questions so far.
Oh, great, great. All right, so what do we do with all this data? The cloud offers another option for this, and that is actually aggregating that data and utilizing it in a system that multiple people can log into. There's a number of systems out there that do that these days. Oddly enough, this is one of the lesser known functions in the world of UAS and photogrammetry and LiDAR processing. So we'll cover this in each of our sessions lightly in the coming weeks. Just want to really thank you guys for joining us today. Please tune in to our coming webinars over the coming weeks. We will be blasting that in the same method we blasted this one. Don't hesitate to reach out, and we will be happy to share this as a downloadable webinar in the coming days.
Yeah, and like
Thanks
I
again.
said earlier too, I just wanted to say, again, thanks for coming. We got pretty much all the questions here, so if there's anything additional, just feel free to, we'll leave this open for a little bit. Type up the question, and we'll either try to answer it right away or email you back. But the next one is going to be inspections. We'll have a couple of use cases of how people are using this stuff in inspections. So if you're looking for more specific information, I would definitely tune in to the coming webinars. So thanks everyone. Thanks Phil, you did a great job.
Yeah, absolutely. And again, we are up against the hours for those of you that do have to leave. But like Mike said, we'll leave this open if you want to type some questions or want us to go back and answer any or go a little deeper on any of this. We're happy to do so.